In our review video tonight, we're going to tackle one of our friendlier topics throughout the year. We're going to interpret some tabular data. The two big things they might throw at us is they might ask us to estimate the slope of a particular function. And the second question they might throw at us, and this is the more common one, is they're going to ask us to estimate the area underneath a curve. And in order to do that, we're going to use either a right Riemann sum, a left Riemann sum, possibly a midpoint, or even a trapezoidal sum. So there's four possibilities for estimating the area there. Now you'll see the common theme here, and this whole idea of estimating is very popular throughout the entire course, and the word estimating is just synonymous with the word approximation, and so they're continuously asking us to approximate certain values throughout the exam. So let's dive in and take a look. So here in our first example, they've given us a function y of t that represents the population of the town over a 20-year period. And so, of course, t represents years and y represents just people. There are no rates introduced into the problem yet. So the first thing we want me to do is to approximate or estimate the slope at 12. Well, the problem is we don't have anything at 12, but and this is a little unsettling, but 12 is not even in the middle of 10 and 13 as far as being the exact average. But the secant line from 10 to 13 is going to be a very good approximation for the tangent line right at 12. So here's what we got. We could say that the slope at 12 is approximately, and here's a good example. We don't want to use the equal sign there. Let's see, we're going to do the y-coordinate at 13 minus the y-coordinate at 10 over 13 minus 10. So we're really looking at 3,697 minus 3,108 divided by 3. And I got about 196.333, so we're reporting all of our answers with 3 decimals. And it's very important to include our label right here, and that would be people per year. Of course, your numerator is measured in people, your denominator is measured in years. Now, they also want us to explain the meaning. Okay, so I want to give you an opportunity here to hit the pause button. Go ahead and write your own sentence. Simulate like game-like scenario here. How would you write out this sentence on May 8th? And then come on back and check out my sentence, see if we were in the same boat. All right, now your sentence, of course, could look a little differently, but it should have all the same key ingredients. We do need to specify, at the moment when t equals 12. So that needs to be somewhere in your sentence. We need to describe that the population's increasing. Okay, and we need to especially use the word rate here, and of course, don't forget your actual answer with its appropriate label. So we should all have the same key ingredients. We might have jumbled it and maybe put things in a little different order, but we should be right around the same boat. All right, now we're going to use the same data here, and we'll consider this part B. And I would never ever expect you to plot these points on a real exam just because it's too time consuming. But I wanted to do it here today just to give you a visual idea of what this trapezoidal approximation is accomplishing. And I think it's very important to be able to visualize what we're doing in order to add meaning and improve our ability to remember it during crunch time. So they asked us to use that table regarding the population of the town in a trapezoidal approximation with 4 subintervals to approximate the average population of the town over the 20-year period. So we're trying to find the average value of this y of t function. So instantly I was thinking of that famous average value formula, integral from a to b, and here we would say y of t dt. So we're trying to find that average value. And we know that when we're all done, our label is going to be just plain old people, because you always get the same label that you started with when you use this average value formula. Now, as far as the trapezoidal goes, and this is unequal intervals. Our first one has a base of 4 units, and what we're doing is we're going to go straight up at 0, we're going to go straight up at 4, and then at the top we're just going to connect them with a straight line. So we're getting, not necessarily the trapezoid that you worked with in middle school. In middle school, your trapezoids looked more like this, of the sort. So now we're rotating at 90 degrees, so it's kind of more upright, like this. So we've got, I consider this height 1, I consider this side height 2, we consider this the base. Alright, so my first height is going to be 2,500, my second height is going to be 2,724, and of course my base is 4 units, and I'm going to go ahead and use those in that formula. So my very first trapezoid is going to be 1/2 height 1 plus height 2, so it's going to be 2,500 plus 2,724 times the base of 4 units. Now, what's the second trapezoid going to look like? Well, let's see. My second trapezoid, real straight at the top, straight here, straight here. It's got a base of 6 units now. Now I would say that the first height is 2724. Okay, we'll call that our first height. And then height number 2 is going to be 3108. So we've got 1/2, we've got our respective heights, 2724 plus 3108, times a base of 6 units. And then I think you could visualize the next two. Now there are no shortcuts to this one because the intervals are unequal. And so we just have to build all 4 trapezoids one at a time. And we'll definitely see some in the near future where the intervals are equal, and then we can kind of cheat, and there are some shortcuts and whatnot. But go ahead, finish this problem off, come on back and see if we get the same answer. So here's what I ended up with, and you notice that I started off, I rewrote my average value formula with the appropriate bounds of 0 and 20, and then we said, okay, we're going to approximate the integral part by using those 4 trapezoids. Here's trapezoid number 1, number 2, number 3, and number 4. And don't forget about the 1/20th out front. I think that may be the most deceiving part. Easy to forget the 1/20th. But one way you can make sure you don't forget it is to make sure that your answer is reasonable. Does this seem like a reasonable number? As you scan your table, does that look like the average of all the y values? And I would say, yeah, that's extremely reasonable. And here's the deal. The AP, when they're grading this, they're going to be much, much more forgiving when you make a careless adding or multiplying mistake if your answer is still reasonable, okay? But if we make an arithmetic mistake and our answer is totally absurd, maybe it's like, 50,000 or something like that, and it doesn't fit the table, then they're going to really hammer us, and we're probably going to walk away with 0 points altogether. So just be ultra careful there. So again, I've kind of ahead of time here. I plotted the points, and I do not want you to do that on an actual problem on the exam. It takes too long. But for visualization purposes, I've done so. And what we've got here is we do have nice equal intervals. And the first thing they want us to do, first of all, notice that we do have a rate of change here. R of t is the rate at which water is flowing into a tank measured in gallons per hour. And so they want us to use a midpoint Riemann sum with 3 subintervals. So my first interval would go from 0 to 4, and then my second interval would go from 4 to 8, and then we'd go from 8 to 12. So let's do the first one. The first interval starts at 0, goes all the way over to 4. We're going to go, now if we're doing, let's say we wanted to do a left Riemann sum, I would go up to a height of 12.5 and straight across. Okay, so if I was doing a left, it would be a base of 4 times a height of 12.5. Now if I was doing a right Riemann sum, I would actually go start with the 4, go up until I hit a height of 13.9, and then go straight across. And you can see now we're overestimating the actual value. So a right Riemann sum would still have a base of 4, but now it'd have a height of 13.9. But the one they actually want here is the midpoint, and so we'll go ahead and oblige them here. What I'm going to do is my base is still 0 to 4, okay, but I'm going to rely on the height at when t equals 2. So I'm going to go up until I hit a height of 13.4 right here, and that's where I'm going to cap my rectangle off at. And you'll see it's a little taller than the left, but a little shorter than the right on this particular example. So for the midpoint here, we've got a base of 4, but a height of 13.4. All right. So now on the second interval, when I go from 4 to 8, the base is still 4, but I'll use the height at 6. And then when we go from 8 to 12, we'll use the height at 10. So those are going to be the respective ones. Now what I want you to do here is not only to finish off the calculations for that midpoint Riemann sum and get the correct label on that sucker, but I also want you to work on explaining the meaning of this definite integral using precise wording, being very accurate and detailed, and we'll see if we end up with the same thing. So here's what my calculations look like. We said that the integral from 0 to 12 is approximately equal to these calculations. We have our heights of 13.4, 14.3, and 14.8. That's the key. We want to make sure we got the right heights. I ended up with 170 gallons, and then my sentence says that approximately 170 gallons of water flowed into the tank from the time t equals 0 until t equals 12 hours. So again, we need to have all the same ingredients. They may be slightly juggled in a different order, but we need to have the same elements. Now, really what we're using here in this particular one is that net change theorem that we saw in Good Morning Math last week. And just to reiterate that if we do integrate, okay, if we have a definite integral and we have this rate of change, we're going to produce an answer that measures the net change or the total change in a certain quantity. Okay, so I hope that helps, and we'll see you guys tomorrow.